So good afternoon, ladies and gentlemen, and welcome to my habilitation lecture titled Learning Body Models from Humans to Humanoids. So I'll start with an example. If I want to reach and grasp this bottle of water, it may seem very easy to you. But notice that it was not always like that. So this is a 3-month-old baby that is presented with an interesting toy. And she sees it and she every now and then touches it, yet she's unable to reach it and grasp it. Okay. So imagine that for the brain, the visual space, the tactile space, the motor space, as if they were all disconnected, and the brain needs to figure out how to connect them and how to act on the world which it doesn't understand. This is a 7-month-old, and you will quickly notice that there is a dramatic difference. So immediately she grasps the toy, there is coordinated action, there is looking, there is reaching. It already seems as easy as it is for us now. Now let's look at the bottom videos. So this is a different task, while that was reaching for an object that you see visually. Now we put a tactile stimulus, a vibrating object, we call it a buzzer, on the body of the baby, like here. And we're interested whether the baby can act on stimuli on its body, whether it knows where its body is in space, so to speak. And you see that she seems aware of the stimulus, and yet she's unable to reach for it or wipe it off, for example. This is a 6-month-old. And again, compare this to a 9-month-old, the same task. First, the buzzer goes on the hand, and in the next trial, the buzzer goes on the elbow, which is a much more difficult location, at least for a baby. And notice again the extremely coordinated reaction. There is looking, there is coordinated action of both arms. So something important the brain has learned in this period, basically from very little capacities to something that almost looks like adult competence. And we would like to understand what happened there. So we can document the progress of the babies. We work with developmental psychologists. You can basically describe the progress the infants are making in these terms, for example. So this is the age of the babies. This is a cross-sectional study. And this is the percentage or the probability of succeeding in contacting the buzzer. So you see, as you would expect, as the babies grow older, there is more success. Some locations are more difficult than others. So this is the elbow. It takes up to 18 months of age to fully master this removal on the elbow. This is just the success. You can also study how the babies do it. So do they look first, or do they reach first, or do they do both things together, or do they use both arms simultaneously, like you saw in the previous video? Now, all that is basically descriptive in nature, and to motivate the rest of the talk, I will help the story with this famous quote of Richard Feynman that was left on the blackboard at the moment of his death. What I cannot create, I do not understand. So how does that translate to our research is as follows. So we would like to understand what is happening here. So what is it that this baby brain and this baby has learned with the help of this baby humanoid robot. So this is the iCap. It's a baby humanoid robot. So its body is built after a child. It has binocular vision. It has, and importantly and uniquely, it has a whole body skin. So it has a whole body sense of touch. So if we tickle it, you see the activation there. And also when it reaches for its body, it feels it. So this is an ideal platform to build what is going on in here such that we can understand it better. So there are two principal directions in our research. One is this: how do we employ this robot to help us understand the baby world? So robots as embodied computational models of child and brain development. And the behavior that strikingly matches the behavior of the infant has been programmed. It has been designed by engineers. So That's fine for now, but we are also interested in basically in the arrow in the other direction. So this baby has figured it out by itself, okay? So it has learned it. It took a couple of months, but it has learned that. And this would be very convenient if engineers didn't have to program robots, program their body models, program their reaching algorithms, because that costs, of course, time and money. So we would like to have robots that calibrate themselves on their own. So this is the other arrow that I will talk about today. So inspiration from nature to give us autonomous, adaptive, resilient, and self-calibrating robots. So the methodology that we're using is summarized here. So we're in the center. These are synthetic sciences, synthetic disciplines, so disciplines that build something like artificial intelligence, cognitive robotics. So we use a number of tools like artificial neural networks, reinforcement learning, and we use robots. So in our case, we use humanoid robots. Here we are at the Faculty of Electrical Engineering, so that's a technical school. So typically we work in this direction, that we use these technologies to create useful prototypes, artifacts, and eventually applications. However, in my research, we pay the same amount of attention to this line of work, where we use the robots, like the humanoid robots, to understand biological phenomena. So to help developmental and cognitive psychology and cognitive neuroscience understand sensory motor development of young babies. This basically is a summary of my habilitation thesis. So there's a number of articles. The ones that are in bold are actually part of the thesis itself, and it's painted here on the same methodological landscape. So there is work that basically spans the whole spectrum. These are basically some book chapters that tell the big story. And then there is work with developmental psychologists where we study the actual babies. And then we use that, basically that feeds the robot models that we're building. And in this case, imagine that, you know, the buzzer task, now imagine that we build models in robots, how to basically learn that behavior. This is the body, the model of the body itself. There is also something called peripersonal space, which is the space immediately surrounding the body, and that is also something that the brain learns to represent. Now, on the application side, learning the body models is basically self-calibrating robots, which is something I will also speak about, while learning about the space around you is something that is relevant for safe, collaborative robots that are aware of the space around them. I will only speak about some parts of this landscape, so those that are labeled in green. So this will be our outline for the talk. So we start first with this direction: how do robots help us to understand infant development? So the task, this buzzer task, involves localizing a tactile stimulus in space, which is this. So psychologist Matt Longo and colleagues, they put together this abstract high-level schematics, how that might work. So to localize the touch in the external world, because for you to reach for it, you actually need to know where it is in space, because also taking into account the position of the limb with the target. So you have the inputs, which is from your skin, which is from your joints, proprioception, also from your muscles. And to arrive at this, you need to combine the inputs with some stored body representations, because the inputs, they do not encode how long your forearm or your upper arm is. So there has to be something that the brain has already learned, something like a model of body size and shape. Now, while the previous was a very high-level schematics, that's not something that you can implement. In our robot, we know exactly how the robot does it, because we programmed it that way. So we know every single detail of this schematics, how, when you tickle the eye cup on the forearm, what it exactly does to be able to localize it with respect to its body frame. So there is the joint angles, there is this stick figure, the kinematic model. Putting these two together is what we call forward kinematics. So if I want to localize the wrist with respect to, say, to my body, I combine the joint angles with this stick figure model. And then I take into account where I was stimulated on the skin. And that gives me basically the extra vector to add, such that I know where in space I was tickled. And then I can send my other arm there, or I can look there. Now, the fact that this works in the robot, of course, doesn't mean that this is how the brain does it. But it's a good starting point. So it's a model that works, and that allows you, or allows us to basically go back to that abstract schematics, look at the commonalities and differences, and work toward a model that might be the one used by the brain. So this is kind of a proof of concept. We know that behavior works, and we can work from here, also taking into account what we know about the brain. And so we teamed up with Matt Longo and developed this new schematics, which is more realistic. It's not the end, it doesn't answer all questions yet, but yeah, it's a nice step in that direction. So I will leave that like that. Now, today I'm mostly speaking about research that has been completed and published. This is one exception. So this is a bachelor project of Ondřej Fiala that is currently running. So we could build a lot of robot models that would be more or less arbitrary. So it is very important to constrain the models in the right way. So one way of constraining them is to provide them with realistic input data. So in this case, we want the baby robot to go through the same experience that the baby is going through. So how do we do that? We have videos of babies using some deep neural network architectures. We extract the skeletons to the 2D pose, and then eventually we can even get the full 3D skinned model of the baby just from that single video. And then we do what we call motion retargeting. So you need to map the movement of the baby onto the robot, which is shown here. And so why is this useful? Now, if you want to build a model that sits in the robot's brain and learns from the combination of tactile, proprioceptive, visual, motor inputs, it's much more realistic if you learn from the same context, the same experience that the baby was going through. And moreover, it's not just the movements. You can also open the eyes of the robot. So this is what the robot sees, but it actually provides us a first-person perspective of what the baby might be seeing at that age. Plus, we have also the robot with the skin, so we can also emulate touch. So we have the right learning material, the right data for the algorithms to learn from. Okay, so this was the arrow, how do robots help psychology? Now, I will look in detail at one of the models where the robot is learning a representation of its skin surface. So many of you may have seen this somatosensory or Penfield homunculus. So there is a stripe of your cortex around here that represents the surface of your skin. Because the density of the receptors, the tactile receptors on your body is not uniform, instead it's much higher on the face or on the hand, you see these characteristic distortions of the homunculus. So a much bigger area of the cortex is devoted to represent these body parts. Now, we have the iCap robot with the skin. It doesn't have skin on the face, though. So we took half of the body, the upper body, and one half, because this homunculus is lateralized, so one hemisphere represents one half of the body. And this is how it looks in the monkey cortex, if you look how the torso up until the fingertips is represented. So our goal is to get something like that for the robot. So this is the training data. So this is, I was stimulating the robot maybe for 45 minutes, just going with my thumb around the robot. Now the skin of the robot looks like this, and so my thumb is bigger than any single sensor. It covers, on average, maybe 6 sensors. And so from that correlation, from that neighborhood relationship, that algorithm, which is a self-organizing map, can figure out what the topology is, so which sensor is next to which. And now, this is already the final product. So after the map has been learned, this is what we wanted. This is the robot tactile homunculus, if you want. So the activations delivered to the robot are mapped onto one artificial cortical sheet homunculus of the robot. So how did we do it? So if you use the standard vanilla SOM, it will not work exactly like this. because every time you use this algorithm, it will end up in a different configuration. There's not enough constraints, basically how to squeeze your skin, which is locally 2D, but it's in 3D world, onto a 2D output sheet. However, in the brain, it always ends up like that. So in every monkey or in every human, the growth topology is always the same, and it is actually genetically predetermined. So we wanted to mimic exactly that procedure, so we came up with this, what we call maximum receptive field size SOM, where we restricted the receptive fields such that what is to become the representation of the torso is not connected to all other parts of the skin, but only to, say, the torso and the upper arm. So this gross layout is genetically, or in this case, pre-programmed, and the fine details are then worked out by the algorithm. So this is the final product. So the color code, basically, this is the output. This is the robot homunculus. The color code represents which part of the cortex of the robot represents which part of the body. And this is a magnification of the torso neurons. So this neuron is this one here, and this is its receptive field. So it learned to represent basically this part of the torso if the robot is stimulated there. So this is one building block that allows us then to combine the different modalities and build basically multimodal body representations. Now I will move to the application side, and that is the robot self-calibration. So the robots learning the models of their bodies by themselves. So standard robot models look a little bit like this. So this is the actual, how it's implemented in the iCap. So imagine a mechanical engineer sitting with the CAD model. This is the CAD model of the robot. Then you impose a kinematic model of the robot, which is, for example, this David-Hartenberg representation, and then you may attach some reference frames. Drawing on these, you have modules that allow you to move the robot to do something useful, like forward kinematics, inverse dynamics, etc. Notice the modular structure. So each of these is basically a software library. These are actual GitHub repositories corresponding to these blocks. Robot models tend to be fixed, centralized, explicit, minimal sensory information, and start from significant prior knowledge. So, for example, the topology is known, and even the initial measurements are typically quite accurate. Calibration is typically performed using external metrology, meaning you come with a device like a laser tracker, you move the robot, you measure the poses, you calibrate. So the calibration is essentially a fine-tuning of parameters. Traditional kinematic calibration distinguishes two methods. One is open-loop calibration on the left, where you utilize something like a laser tracker or a camera that observes the poses of your robot, and closed-loop calibration, where you, for example, attach the end effector to a table, and then you move the joints, and because you know that this is fixed, you can use that to calibrate. Both these methods employ some what is called external metrology, so either something in the environment that is physical or this laser tracker or device like that, which of course is not always very convenient. Now, current robots are made often from plastic or from elastic materials, so the Pepper robot here is a good example, meaning that they are not very accurate. On the other hand, they often come equipped with a set of affordable but increasingly accurate sensors like cameras, tactile, force, inertial sensors. So again, notice how many sensors the Pepper has. So these two things together, they create a necessity and an opportunity for autonomous continuous recalibration, meaning you cannot afford to always come with a laser tracker to calibrate your Pepper. You need to do it on the run, but because it has all these sensors, it is actually possible. So this slide illustrates work that we have done maybe in the last 5 years that does exactly that. So we're using humanoid robots, and they do either self-contact or self-touch or self-observation, self-vision to calibrate their kinematic models. So for you to calibrate, you always need redundant information. So say if I touch here, my left arm sort of predicts where in space that point is, and the same for my right arm. But because I know on the skin where it is exactly, there might be a discrepancy, which I can use as an error term to improve the calibration of the robot. The same is true for self-observation, and in fact, these two can be combined. You can use this for humanoid robots. You can also turn the problem around. So what we did here is that we received the now robot that was then retrofitted with the ICAP skin. We didn't know the spatial calibration of the skin, so we used self-contact to calibrate the skin. And finally, here we show that it can work even for an industrial robot. So this is a dual-arm manipulator, a Motoman. We put two cameras, and we put a device like two spheres that provide this contact constraint. And we demonstrated that you can actually calibrate this industrial robot using this self-contained approach as well. So this is schematically illustrating the self-contact, and this would be the self-observation. So imagine you close your eyes, you imagine where your fingertip would fall on the retina, and then you open the eyes, and it's a little bit, the position is slightly different. So that's something that you can use for learning. And it proved advantageous to put combine all these methods, so put them in one cost function. So this term represents the self-contact constraints, and these are the self-observation terms, how you see your arm, left or right arm in the left or right camera. So they can be all put in a single cost function. And we also show that the more methods you combine, so for example, this means left arm, left eye, and this means left arm, and left and right eye. So all these chains crossing together, the error after calibration gets smaller. And we can also show that in terms of observability and identifiability of the parameters, it's advantageous. So there is a synergy the more of these chains you combine. And that actually is quite natural. But yeah, the more sensors you have on your robot, the more you can do these kind of things. And we made available a MATLAB toolbox that can be used for all these things. So, as I said, the robot body models tend to be fixed and using little sensory information. Here we showed that you can make it more adaptive and more multisensorial, so in this case using vision and touch. Yet this is still quite modest compared to what animals can do, right? So as you know, they use tools. This is a crow that not only uses tools, but makes tools, so you can look at a tool as an extension of your body. But it's not just that, you also need to learn how to use that tool. So it's very complicated, and it's amazing, how the animals perform. So we are still very far from that with our robots. These are dogs that were either lost or were born without limbs, and yet they can learn to adapt and to locomote. So this kind of level of adaptation and resilience is still completely unmatched by machines. So that's our inspiration. So coming back to the previous schematics, I put some other works from robotics that I will not go through. So they all strive to make robots adaptive, to calibrate themselves. But still, animal and human brains and their level of adaptivity is much, much bigger compared to what we currently have in our machines. There's also other characteristics of body models. That I will explain briefly. So the robot, that the model is explicit, that means that, for example, in this is the model, this is the robot. You can find one number that corresponds to the length of the upper arm, for example. If you want to look for this in the brain, it's unlikely to succeed. So there wouldn't be any single neuron or you wouldn't be able to single out a representation that represents the length of the upper arm in the brain. So the bottom line is that brains represent the bodies in largely exactly opposite ways compared to robots. So veridical, meaning it's a true model, it corresponds to reality. This is not always the case, for us, because ultimately what is important is that we can successfully act. It's not important that the model is actually veridical or correct in a geometrical sense, for example. Centralized, meaning one model for a robot, universal, modular. So you see these modules here. And for the human brain, it has largely the opposite properties. For the octopus brain, it would be the other extreme, but I didn't have the time to talk about the octopus. But it can be a nice source of inspiration. Okay. Now, if we now take a look at it from the engineer's perspective, so which of these, we know now that brains represent bodies differently compared to robots. So which of these properties do we want to take on board? So some of them, like adaptivity and multimodality, we are ready to just take them on board. It's relatively straightforward, and it will make the robots better. So that would be this direction here. Now, the other properties, we will have a harder time. So do we want to give up modularity, this centralized nature, explicit and veridical character, serial operation? So it's going to be hard. It's really at odds with engineering practice and intuition. But if we want to get truly resilient machines, we may have to give up some of these convenient properties. So, and in the end, it's action that matters. It's not the quality of a model per se. And the other thing that we can look for in nature is that there is always many suboptimal solutions ready. So none of them may be optimal, but there's always a lot of them available. So if something fails, there's always an alternative. So that's something that we want to also have in robots. Yeah, more details about these characteristics of the body models are in these two recent book chapters, which are here. Okay, so to wrap up, so the standard model of a robot, which would be here, this represents forward kinematics, would be fixed, explicit, unimodal, so using just one sensory channel, for example, while the brains and their body representations, these are areas in the brain that are where we expect something body-related to be represented. They are at the opposite end of the spectrum. And now we want to move this way, so making the robot body models more like this, for two reasons. One is we want to understand what is happening here, so this becomes our model of the body representations in the brain, an embodied model. And we want to have robots that better perform, so in terms of autonomy, robustness, safety. So with this, I would like to acknowledge my group. So I'm really proud of how the group, the number of robots and people has been growing over the years. And I want to thank my Department of Cybernetics. Also the previous department had, when I started in 2017, Jan Kibitz. And two people I want to explicitly mention. The current department had Tomáš Svoboda. So the independence that he has granted me, combined with the mentorship and support, is really unique. And Petra Ivaničová, who takes care of all the administrative and financial matters, so we can focus on our research. I thank our funders, and I bring up this last slide. This may look like self-promotion, but I was asked to do this because that's part of the habilitation procedure, so here is the slide. Thank you for your attention.
Thank you very much for very nice and interesting lecture on humanoid robots learning from human body models. Now I'm open public discussion and ask the audience for putting questions. Maybe, yes, please, Professor Kittler.
Thank you very much for fascinating lecture. My question actually relates to some other research that I looked at by looking at your application, which relates to quadruped robots, and in particular estimation of stride. And I saw that you are using sort of heuristic features for the regression problem that you are solving, and wondered what prospects there are for deep learning techniques that would actually learn what features to use by training end-to-end.
Right. Okay, so you're referring to, I think, work from Zurich when we used the dock robot and we did basically path integration or dead reckoning, that the robot was integrated in the path. It's work from 2012 or so. So back then there was no deep learning, and when we used some standard regression to learn that, and I think you can try with deep learning and maybe even like some networks that could take the temporal component like LSTMs into account. But it's this work I sort of left behind, so I'm not continuing that.
Okay. No, I just wondered whether there were some reasons like lack of data that would prevent you from doing something.
No, I'm focusing on the humanoids now.
Yeah. Okay. Thank you.
Professor Železný.
So I think you said that the main reason you're doing this is to get more understanding of the biological systems, right? So is there any example you could give us where in your research actually provided such a biological insight?
Mm-hmm. Okay, so that's a good question, and it's not easy. So we work with some of these psychologists maybe for 5 years now. So it really takes time to sort of develop that they understand what does the robot bring to the table, so to speak. One example is actually on this slide. So this is work of Zdeněk Straka in collaboration with Jean-Paul Noël that was published like a month ago, where we modeled the properties of the peripersonal space. So the peripersonal space is this space around the body. It's a sort of protective bubble, and it has specific properties. So if something flies toward you with a certain velocity, it activates more. So you can measure that in the brain. So you're predicting impact, essentially. If it's a dangerous object, if you compare a spider to a butterfly, it will fire even more. So you basically get ready for some defensive action. So what we did in this work, we developed a normative model of that encoding using basic Bayesian decision theory. So we modeled certain costs associated with something, if something hits you, if you predict it or not. And we can explain a number of empirical data where they have psychometric curves where they measure exactly that. So if an object comes toward you, away from you, dangerous object, not dangerous object. And we also making predictions for new experiments, for example, that people should measure the uncertainty associated with perception, and that all maps in different ways onto the psychometric curves that we could obtain through our model. So if you want an example, then this work I think is in computational biology is a good example.
Okay, so I'm interested in the practical application. So you have already solved or almost solved the problem of self-calibration, if I understand well. So what remains to be done? What are the big challenges that you want to address in the future?
Right. Okay. So as I was trying to explain when talking about the animals afterwards. So in all these cases, we start from a very good model. The topology is known. The initial accuracy is sort of okay, and then we can improve the model. But this is still very simple compared to what animals can do. So for example, there are things like, so the brain seems to be very adaptive, very plastic, but also very liberal about its body model. So there is this so-called Pinocchio illusion. If you hold your nose and somebody vibrates the tendon of your biceps, you get the illusion that your nose is 0.5 meter long. So, which seems stupid, but it illustrates how plastic the brain is, and that allows us to cope with all kinds of things. You get a new tool, or you're injured, and all these things. And so that's something that would not happen to the ICAP under the current framework. So the ICAP would not start thinking that its nose is half a meter long, because we have all these constraints and because the model is set up in a different way. So we want to somehow get rid of all these nice engineering models and constraints and try something more crazy that would be as adaptive as the brain.
Thank you. You have mentioned state estimation on several occasions, on several slides. So I was wondering what kind of state estimation algorithms are you using for the estimation of pose of the elbows and...
Right. So normally we use some, Bayesian estimation. So kind of some standard filters. Depends. It's not really an important part of so. There's research on biology that the brain in many ways estimates optimally if you, for example, combine a visual and tactile modality about, let's say, the location of your hand, that it performs base optimal estimation comparing the variance of the two modalities. So that's basically the direction we're going there.
Okay, so any Bayesian filter like the particle filters or things like that?
For example.
Because for that you need a precise model, including specification of the noises, densities, and so on. So you need a high-quality model for that. Otherwise, you can use like Kalman filter-like algorithms. So
yes. So actually, it's a little bit visible here. So this original schematics, how the brain might be doing that, sort of combines body models and body states. So in this new version, we split them. So one thing is your body, long-term body model, so how long is your forearm, and the other thing is your body state, so where is your forearm currently in space. So these are two different things. So in the self-calibration work, we typically learn the long-term body model, so basically how long my forearm is all the time. While the state estimation for that, you need some kind of filter. So there are people using particle filters, Kalman filters. Yeah.
Okay, thank you.
Thank you.
This was a nice lecture. May I ask also for the self-calibration? I am curious because there is obviously, as you said, the gap between robots and humans and animals. So this gap is due to the algorithms and also due to the spatial, let's say, resolution of tactile sensors, or let's say, or also other sensors. Or is it just algorithms?
So. Okay, so the humans and animals, they still have better hardware, so they have better bodies than we have. So the ICAP has 4,000 tactile receptors on the whole body, which is a lot, which is great, but it's still very little compared to what we have. But I don't think this is the main problem. I think that it's a completely different approach that we're using. And so I think it's really the algorithms. So we want to basically try to replace all the nice engineered models with something brain-like that is more messy, but I think it has more potential.
Mm-hmm. Thank you.
So do we have any other questions? Maybe I have one. You started with robots learning babies' body models. Would it be possible to start with the adult body models, as some adults declare that their movement is efficient, nearly optimal? For example, my wife says that when she's cooking in the kitchen, she says, "Don't get in my way here. I'm not so efficient." So the question is to learn from optimal movement models.
Right. Sure. So the majority of literature on, for example, this tactile localization or on motor performance is indeed in adults. For example, we're just now starting also this buzzer task on adults in our lab using a motion capture system. So we would like to learn how exactly adults do it. But I mean, that's more of a philosophical sort of stance, but some people argue that for you to understand the final product, you need to understand its development. So that's why we focus on babies.
Thank you. So if we don't have any other questions, I would like to thank the presenter and the audience for asking questions. And I close this public discussion, and we will continue with the formal habilitation procedure in the room number 80 after a short break.